being here tonight, this great venue. I'm going to introduce the CEO and Director of the Bayou Vermilion District, Dr. Sherman. He just has some opening remarks and welcome. Thank you.
Thank you very much for everybody being here tonight. Bienvenue à Vermionville. On est très content de voir tout le monde là, ici pour la présentation ici sur le parc sur l'eau, sur la recherche. I'm very happy to see everybody tonight for this presentation about the water research part. I know Emile and his crew and Emile Osele, we've been working on this for a long time. I know you've been working on this for a long time. This has been a vision we've had here at the Bayou Vermilion District for several years, but of course, as many of you know, the flood of August of 2016 was a wake-up call for a lot of us here, and I think people starting to understand the importance of water in our area. Go figure, we're living in a swamp and people just now realizing that water is important to us, you know. Unless it's in your living room, I guess you don't think about it. But I want to thank everybody here for being here today. It's a wonderful turnout, and I can't wait to see what they came up with, and hopefully they'll use all these ideas when our new buildings will be going up on the end of the parking lot, and put the Bayou Vermilion District into the kind of organization that the parish voted for to have here in with the millage to have here, not in addition to Vermilionville preserving our heritage culturally, but preserving our heritage of the environment is also very important. So thank you very much for being here, and I hope you enjoy the presentation. I look forward to seeing what y'all have to say also, so thank you very much.
Thank you, Dr. Sherman. I'm going to stay on the floor and make my remarks. Thanks again. I'm sorry, though. We're not event people.
I bet I don't need it. There's a lot of people to thank tonight. It's a beautiful venue, very unique. Another unique aspect of our project this year to senior design was VVD acting as our client. We've never had a real-time client experience with senior design, and it's proven, I think, very, very valuable and quite a learning experience. We owe a big round of thanks to Emile and Lauren and Wes. They've been great fielding questions. They've come to campus, they've come to class, they've interacted with the students, helping us make decisions, just like engineer-client relationship, and I appreciate it. They've tolerated us coming here, doing surveying, so I just thank you. Senior design could not happen without our professional engineering people. It's that simple. They're critical to the process, to the learning. There's so many aspects. Not one instructor couldn't come close to being able to give experience for all the different aspects. And they are faithful, true blue, every semester, every group. And I always like to recognize them. They don't like being recognized, but I appreciate it tonight. So with us tonight is Chris Richard, Romaine Zago, Glenn McCall, Mr. Maker, Colby, and Megan Foray with U-Ball. Am I missing anybody else? Mitchell Rise, but thank you all. Also tonight, I'd like to recognize the faculty that's here. It's been a long process for the students and for the faculty, but I know I can speak on behalf of the faculty about how proud we are. Specifically this class. It's a big class. They're a great class. They've provided extraordinary leadership through their time here. I'm very proud. I feel very close to most of them, and I'm both glad to see them graduate and sorry to see them graduate. But I know I speak for the faculty. So, faculty, please get a chance. Parents, friends, you may have heard the horror stories. You may have a chance to put a name with a face tonight, but please take the time to thank the faculty if you get a chance. Last, thank you all, families, friends. I know it takes a support system, right, for everyone to make it through a college experience, whether it's financial, emotional, all the things that go into it. I know it couldn't happen without the support of loved ones for all the students. So we're very appreciative tonight. Let's enjoy this great venue, enjoy the presentation. I'm now very pleased to introduce Mr. Dustin Giddard. He's the peer selected project manager for the senior design project.
All right, good evening, everyone, and thanks for coming out to Vermilionville. Is this on? Can you hear me? Okay, so thanks for coming out to Vermilionville, to their Performance Center for the 2019 Senior Design Capstone presentation. Now, again, my name is Dustin Giddard, and I'm the project manager for this semester's design team.
I'm Carolyn Chapman. I am the Water Resource 1 team lead, and this is our team. I'm Mary Grace Sherlock. I'm Alice Earl.
I'm Willie Murley. I'm Jack.
I'm Jordan East, team lead for Water Resource 2 and the environmental team. This is our team.
Spencer Johnson.
Franz Fire.
Avery Joseph Brooks.
My name is Brian Freehold. I am the construction team lead. This is our crew. I'm Michael Broadax. Justin Abeck. Mario Zabadir. Rob Sonic.
Finally, I'm Chase Kramer, and I'm the General Civil and Geotechnical Lead. And this is my team.
Nicholas Castor.
Cameron Oakland.
Evan Sochet.
All right, so this semester's design group has teamed up with Bayou Vermilion District to help with the design and development of their water research park. Bayou Vermilion District is an organization that was created in 1984, and their purpose is to beautify, manage, and preserve the Vermilion River and Lafayette Parish. Their mission focuses on the environmental and cultural aspects of Lafayette. On the environmental side of their mission, Bayou Vermilion District removes trash and debris from the river, as well as works with local government to measure the water quality and river stage of the Vermilion River. On the the cultural side of their mission, Bayou Vermilion District opened up Vermilionville Living History Museum and Folklife Park in 1990. And since then, the park has become one of Lafayette's premier tourist attractions, welcoming over 60,000 visitors per year. So Bayou Vermilion District has put a lot of work into their project, and they have a vision of what they want to see the water research park to be. So when they came and introduced the project to us, they had a packet full of all of their purpose for the park, their water flow features, as well as all the structures and the designs of what they wanted to see in a park. So we took that as a great guideline to move forward with in designing these features. So according to Bayou Vermilion District's Department of Water Quality, some of the purpose of their parks are to improve the existing water features by introducing water movement throughout them, which will actually eliminate some of the need for chemical maintenance. They also want to create multiple educational and demonstration areas throughout the park, as well as a new watershed exhibit, and they want to build a water quality laboratory to measure the water quality of the Vermilion River. Bayou Vermilion District expects the Water Research Park to bring in about 100 visitors per day. So there's a couple of issues that stem the idea of creating a water research park. The first one is the water quality of the Vermilion River. So the Vermilion River contains lots of trash and debris. It is very high in total suspended solids, total dissolved solids, and high in fecal coliform. And it also has low dissolved oxygen levels. The Louisiana Department of Environmental Quality actually lists the Vermilion River watershed as an impaired waters. The second issue was the existing water features within the park. As you can see here, the aeration pond and the Petit Bayou, both of these existing water features, they get supplied water from stormwater runoff, and the only way the water actually leaves the park is by being pumped into the Vermilion River. So during dry periods, the water is held up within these ponds with little to no movement, and the water becomes stagnant, which contains low dissolved oxygen levels and provides an environment for invasive plant species to thrive. So once we were introduced to the project and we took the information that BVD gave us, we got to work as a class, and we came up with some objectives on what we wanted to do as far as designing the water research park. And one of the first things we did was we determined the watershed that flowed into the property, and we analyzed the stormwater runoff characteristics and how they actually affected the water research park. Second thing we did was we designed all the water flow features throughout the park, as well as determine the flow rates that go through them. We designed and analyzed all of the structural features throughout the park, along with their foundation systems. And we also designed other features throughout the park while optimizing space in certain areas of the site. We researched and determined the permits required to build the Water Research Park. And lastly, we came up with a cost estimate on how much we think the Water Research Park is going to cost to build. So besides what we got from BVD, we actually sought out some additional resources to help with our design. And one of the first things we got were the original plans for Vermilionville from Domingue Zabo. We also got the proposed Water Research Park building from architect Lynn Guidry. We received some site survey information from Spec Engineering and Lafayette Consolidated Government. And we also received all of our LiDAR data and subsurface drainage maps from Lafayette Consolidated Government. All of our water quality and river stage information came from USGS. So although we got a good bit of information, there was still some gaps in that information. So luckily enough, we were close enough to the BVD property to come and perform multiple site visits, where we were actually able to survey do our own site surveying. So through these site surveys, we're able to determine elevations of critical points throughout the site, determine the elevations of the existing water surface, as well as determine the depths of all the water features. So one of our biggest challenges in designing this Water Research Park was taking the vision that Bayou Vermilion District had and creating viable design features. So we created options for all of the flow-through features. We actually looked into stormwater diversion and detention. We came up with options for all of the structures and as well as site layout. And we presented those to Bayou Vermilion District throughout the semester and the design process until we were able to finally figure out exactly what the final design feature was going to be. Now we did encounter some site limitations, some physical limitations, regulatory as well as client-imposed limitations. Because Bayou Vermilion District is right on the Vermilion River, we had to be mindful of the floodway and flood zone. The floodway and flood zone actually dictated where some of our structures were located, what type of structures we were able to design, and what finished floor elevations these structures were to be designed at. Also because of the variation in the water quality coming into the park that we're going to be pumping in, also the stormwater inflow into the park, and because the park is primarily going to be used for educational purposes, we did not design to meet effluent standards as you would typically see whenever you're designing a water or wastewater treatment plant. So I'm going to go ahead and give you a general site layout. This is going to show all of the features we worked on, and it's also going to provide a sequence for the rest of the presentation moving forward. So on the west side of the park, we're going to we designed a pump station that's going to pump water from the Vermilion River and into the park. The water will then flow into this channel, a portion of which is existing and a portion of which is going to be newly constructed. South of the channel is the swamp, and this is going to serve as a detention area for a large amount of stormwater runoff. The water from the channel and the swamp are both going to flow into the aeration pond, where we also have designs for a fishing pier, a pedestrian bridge, and some improvements to the drop pipe. From here, we're going to talk about some improvements to the existing roadside ditch, and water will flow through the Petite Bayou and discharge back into the Vermilion River through our passive outlet. Finally, we'll come back and we'll talk about the Water Research Park building, the new parking lot layout and design, and then the walking paths that are designed throughout the site.
The Vermilion River will serve as the primary water source for the Water Research Park. Using the United States Geological Survey's river gauge operated at the Surrey Street Bridge and the Vermilion River crossing, just near the northernmost point of our site, we obtained water quality information as well as river stage information on the Vermilion at this point. The turbidity of the Vermilion River is the measure of the clarity or the overall cloudiness of the water, which can be caused by suspended materials such as clay or silt. We conducted our own 2-column settling tests on the Vermilion River water quality to determine if it had any settling characteristics or capabilities that we could reach within the park. We did observe over 124 hours of the settling test, or approximately 5 days. We left the water undisturbed. where we noticed a drop from 80 FTU turbidity to approximately 24 FTU, which falls within the annual range of about 20 to 300 FTU that we saw from this April to the past April. So although we did see a drop in the turbidity from 80 to 24 FTU across that 5-day undisturbed settling period, we did not observe very much change in the aesthetic quality or the overall clarity of the water. Therefore, within the limitations of our design of a flow-through system, we do not expect the turbidity to be affected within our system. The 2018 Louisiana Water Quality Integrator Report concluded through LDEQ that the highest level of impairment across Louisiana water bodies was due to low dissolved oxygen levels. Low dissolved oxygen levels in the water affects aquatic life by limiting life-supporting functions such as photosynthesis, as well as respiration. Looking at the temperature and dissolved oxygen graphs for this past year from USGS, we can see a trend in warmer months and at higher temperatures. We see a drop in dissolved oxygen levels, whereas in colder months, we can see a rise in the dissolved oxygen levels within the river. LDEQ does recommend a minimum of 5 milligrams per liter of dissolved oxygen to be met in fresh waters. This is a recommendation that we would like to obtain within the park, especially in summer months when the water entering the park from the Vermilion River does fall below this 5 milligrams per liter.
When evaluating our site, it was important to get a feel for what the watershed or the area that would funnel stormwater into our site was and what the associated flow rates might be. Now, our watershed covers an area of 123 acres and can be divided into 5 sub-watersheds that we're referring to as zones 1 through 4B. Now, zone 1, shown here in red, is our largest zone. It covers approximately half of the total watershed. The other 4 zones come in between 11 and 17 acres apiece. Now, just to select our design storm and to develop a methodology for calculating flow rates, we refer to the Louisiana DOTD hydraulics manual. And for our design storm, it's going to be defined by 3 parameters. The first is the return period, or the expected frequency of occurrence. The second is the duration, and the third is the intensity. Now, the Louisiana hydraulics manual requires that for a site of our size and our purpose, we have the storage capacity to handle a 25-year event, the culverts on site being able to handle the flows from a 10-year event, and that we evaluate the site as a whole for a 100-year event, although we don't specifically design for a 100-year event. This serves the purpose of providing awareness to all stakeholders as to what the effects of a more rare but more extreme event might be. For the duration, the length of our storm, we use a property called time concentration, which is simply the time it would take a single drop of water falling in the furthest reaches of our watershed to travel all the way and arrive on site itself. Now, zone 1 is our largest zone, and to ensure that we get contribution from the entire watershed, that serves as our time concentration calculation. So using a combination of the Kirchhoff equation for overland flow, Manning's equation to calculate flow through subsurface pipes and through an open channel, we arrived at a time of concentration of 30.5 minutes. That will define the length of our storm. Now, we referred back to the hydraulics manual for the intensity, duration, frequency curves, or IDF curves, to calculate our intensity. And for our 25-year event, we arrived at an intensity of 5.2 inches per hour. And then using the rational method, again, dictated by the hydraulics manual, we calculated peak flow rates for all zones, for all storms. You see here an example calculation. So zone 1 sees 170 cubic feet per second for a 25-year event. And this slide has a list of the peak flow rates from every zone and for all 3 of our design zones. And that gives you a comparison, or a relative comparison of how these flow rates change with more intense events. Finally, we constructed hydrographs. Now, hydrograph is just a chart that shows the change in flow rate against time. And so if you look at the top left for zone 1, at time 0, the start of our storm, the flow is 0. And then increases to our peak rate at time of concentration, the end of our storm, and then trails back off to 0. The other 4 zones have a slightly different shape. That's because of their smaller size. They have a quicker time of concentration, so they reach their peak sooner, hold that as a plateau, and then when the storm's over, they decay themselves. We then took all of this information and input it into our hydraulic modeling software to estimate or predict the effects of these storms, but that will be discussed in greater detail later in the presentation.
After determining the amount of stormwater that would be entering our site, we needed to design the amount of water that we could pump from the Vermilion River and through all of the features within our park. To do this, we took one-to-one cross-sections as seen here and took the cross-sectional area of all of the cross-sections to determine our limiting factor. This was found to be the ditch entering Petite Bayou. With that information, we then went through iterations of different velocities, taking into consideration erosion protection, weed prevention, as well as the client's desire to move water through the park. We came to a conservative velocity of about 0.5 feet per second with an approximate flow rate of 3,300 gallons per minute. The graphic shown here is a fire hydrant that's pumping about 1/3 of what we plan to be pushing through the park. That's just to give you an idea, which you can't see, sorry. We also needed to determine the floodplain delineations within our site. Shown in the red hatched area here is what is known as a floodway. There are very strict construction limitations when building within a floodway. So we tried to steer clear of that, even though we worked with it. The green area shown here is known as flood zone AE for our particular property. This is defined by FEMA to be a high-risk area for a storm of 100-year frequency. Return period, and has a base flood elevation of 15 feet, not the 88.
So I'm pretty pumped to tell you all about this next part of our design. So after we came up with our design flow rate, the next thing we needed to do was to figure out what type of pump we needed and the location, as well as the type of structure to protect that pump. So if I direct your attention over here, denoted by this blue circle, this first option was a submersible pump with a wet well design placed inside of the floodway. And here, denoted by the yellow star, was an above ground structure with a suction lift pump outside of the floodway. Now after speaking to BVD, we decided the best option and the best design was the submersible wet well with the submersible pump with the wet well, due to its economical design and best design. So here's a typical cross section if you were facing east. Here's the Vermilion River. The water would be gravity fed through this pipe here and into our wet well. Additionally, the water surface elevation dictated in the river, or in the river, would dictate what the water surface elevation in the wet well would be. And once the water is here, it will be pumped from our submersible pump up here and into our proposed channel. And additionally, if we ever needed to cut off the flow of the water from the Vermilion to our wet well, we install a valve right here. We chose the invert of this pipe here to be based off the 10th percentile water surface elevation of the Vermilion River. That way our clients can utilize their pump almost 90% of the time. We got that data from the USGS Surrey Street gauge and correlated the elevations accordingly. Additionally, we needed to size this pipe in order to give us our design flow rate here. We need this pipe to supply enough water for that flow rate. To do that, we used everyone's favorite equation, the Hazy-Williams equation, with the frictional losses and the minor loss equations to come up and iterate to find an adequate size of 18 inches. We double checked that and it came out to that it will supply our pump. Next, we need to figure out what type of pump we need. So, using our design flow rate as one of our parameters, we next needed to come up with the total dynamic head to input into software. To do this, we'll back up a little bit. So, total dynamic head can be considered the amount of energy that a pump needs to push the water or pump the water from the wet well up out into the channel. To do this, we used the same equation, Hazy-Williams, with the frictional loss and the minor loss equations, and came up with a value of around 12.5 feet. We then plugged in our 3,300 GPM and the 12.5 total dynamic head into the software here and generated this pump curve and selected a submersible pump manufactured by Pentair Fairbanks. It is also a 15 horsepower pump to use in our wet well.
Through finding our operational parameters, we were able to make sure that the pump could ensure that they won't flood the site. They won't cause cavitation within the pump, and that they won't overheat the pump. The pump is going to be going 8 a.m. to 4 p.m. Monday through Friday. Whenever it rains, we ask that the maintenance shut off the pump because we do not want to overwhelm our system with excess stormwater. We also wanted to narrow down our operational restraints by picking a minimum and maximum water surface elevation in the river, which is also the same water surface elevation in the wet well, to find our minimum and maximum flow rates and total dynamic heads to make sure that our pump will not be overheated or it will not cause erosion throughout our system. Our minimum water surface elevation is denoted by this line right here is 2.65 feet. Anything below 2.65 feet in the river needs to shut off. We need to shut off the pump because it will cause overheating in the pump. Here is the maximum water surface elevation of 9.98 feet. This will provide a maximum flow rate of 3,450 gallons per minute, which is greater than our design flow rate of 3,300 gallons per minute. Knowing our maximum flow rate, we then had to make sure and prove that this flow rate will not scour or cause erosion through our limiting cross section, and through calculations, we did prove that to be true. So starting our system, we place a 18-inch ductile iron pipe in the Vermilion River at 2-foot elevation. We make sure not to encroach upon the right-of-way of 100 feet set by the Army Corps of Engineers. This pipe is 150 feet with a 0% slope, and to prevent the pump from being damaged by the debris, we designed a T-shaped screen that has a spacing of 2 inches. This is to prevent the maximum debris from getting into our pump. Also, we increased our diameter of our screen to slow down the velocity so that debris does not get matted up against the screen. So moving through from the Vermilion to our wet well is our trash rack. This aluminum trash basket will meet the inlet so that any of those excess debris that got through the system, the 1-inch spacing will catch that. This trash rack is very durable and can handle heavy duty applications like the Vermilion River.
So the functionality of a wet well is to protect our pump, ideally, and to supply the water that we need for our design flow rate to our channel. Here we have depicted a typical wet well with a hatch and a vent here. We chose our inner diameter to be around 84-inch to allow for minimum clearance for our pump in case of maintenance needs. Additionally, is a reinforced concrete structure, cylindrical in nature, and extends down into the ground with a square foundation. We found that we need to excavate around 15 feet, and that our square foundation would be 10 foot by 10 foot by 1.5 feet. Right here is a typical construction of a wet well, as you see here. Force during a flooding scenario, and we found the force to be around 9.7 kip feet and distributive loading, as you see here. So then we used ACI 318 concrete code to design the reinforcement, checking the necessary minimum steel requirements and max spacing requirements.
Through finding we designed our wet well cover for only pedestrian use only. So these are 300-pound per square foot load-weighted doors, and they are made from aluminum I-bar grating, and they're hinged with stainless steel bolts and supplied with a positive latch. As you can see in this visual, the door will open, and under the door will be a grating. In case someone were to fall, the grating would catch that person. And ending from our wet well to our channel, there will be a 50-foot pipe of 12 inches, a 50-foot PVC pipe of 12-inch diameter, which pushes a fast velocity of 9.35 feet per second.
So the purpose of the channel is to serve as a pathway for the Vermilion River water to travel from the pump station to the aeration pond. Our total channel length is 500 feet. This includes 250 feet of our existing channel, as well as 250 feet of our new additional section to this channel. There will be a 90-degree turn at the midpoint of our channel. Pictured here is the proposed location of the new section. So this will be a trapezoidal design with a 2-to-1 side slope, a top width of 9 feet, and a bottom width of 3 feet. Our depth will be 1.5 feet, and our channel slope will be 5%. 0.5%, excuse me. So we designed our entire channel to be uniform throughout. This will require cutting the new section as well as filling the existing channel with additional soil to minimize the current dimensions. It will also require clearing and grubbing throughout the entire channel. If the possibility of erosion, when considering the possibility of erosion, we propose that riprap would be incorporated in the lining of the channel at the inlet and the 90-degree turn, due to these being the most critical points of the channel. Here we use the Manning's equation to verify that our channel design could handle the maximum possible flow rate of 3,465 gallons per minute.
Here shown is the swamp location. It will serve as temporary detention for the stormwater that will enter the park through the 54-inch pipe. This was the 170 cubic feet per second denoted in the watershed delineation. Currently, 3 sides of the swamp are well defined, and we propose that a 1-foot berm along the northern side of the swamp be constructed for the completion of the detaining structure. The current channel will need to be cut off. The existing channel that runs parallel to the Eshop Trail here will need to be cut off to ensure that we do not feed stormwater into our new channel. A planned profile view of this cutoff is shown here, and above is a cross-sectional view of what this purple line is here, of the berm with the channel having a shared side slope of 2-to-1. So we chose to use reinforced concrete box culverts as our outlet from the channel and swamp to the aeration pond.
When designing for these features, we were faced with a few vertical challenges, such as the water surface elevation in the aeration pond, as well as the clearance needed for the asphalt roadbed. In order to accurately design for the hydraulic and roadway designs, we could not use a typical culvert or even an arch design. So we have from the from the channel to the aeration pond, a 1.5 by 3 foot culvert, and we have two 2 by 5 foot culverts from the swamp to the aeration pond. These will all three have an approximate length of 45 feet, and we use the Manning's equation once again to prove that our designs could adequately handle the maximum flow rate of 3,450 gallons per minute.
Since the roadway would need, the maintenance roadway that runs from Fisher Road northbound to the maintenance buildings on the premises would need, portions of it would need to be removed to place these concrete box culverts. We propose removing and repaving and regrading the current maintenance road. As you can see, the current profile of the maintenance road, starting at Fisher Road, which is the public road that runs along the southern border of the Bayou Vermilion District property, has an elevation of 10 feet. Moving northbound, the elevation drops to a 8.17 feet and then rises slightly again to 8.3 feet back by the maintenance buildings. If we could repave the road starting at elevation 10 from Fisher Road back to 8.3 at the maintenance buildings, we would be able to overcome the vertical challenges faced for both the hydraulic structures and the requirement of the asphalt roadway. This will also create a smoother ride for all through traffic, including the maintenance vehicles as well as garbage trucks.
Following the water's flow through both the channel and swamp areas of the park, it then enters the aeration pond, which not only passes the water through the park continuously, but also features a fishing pier and a pedestrian bridge, as well as an existing drop pipe. Just adjacent to the aeration pond, in 2017, there was a geotechnical investigation conducted by Louisiana Testing and Inspection. The results of this inspection were used for all geotechnical calculations throughout the course of the project, and indicated that there was a silty clay layer down to 27 feet below grade and a dense sand layer from 27 feet to 50 feet below grade. The results of this investigation were used for settlement, bearing capacity, lateral earth pressure, skin friction, point bearing resistance calculations.
So to continue our site investigation, shown here in red is the proposed area for the pedestrian bridge. This was the location the client proposed to us. It was the most logical, seemed to be the most logical location because it was the shortest span. Now, although it did arise several issues. Shown here in the bottom picture, we would have been forced to remove several mature cypress trees as well as the existing parking space. So, after a site visit and several discussions with our client, we decided that this location shown here in yellow would be a more adequate location. This location allowed for the space to construct the bridge properly, as well we would not have to remove any cypress trees or lose any parking area. So now that we have the horizontal location of the bridge, we turn our attention to the vertical location of the bridge. There was two requirements that we considered for the vertical location. First was the hydraulic features flowing beneath the bridge, and second was a client request to continue to allow kayakers to utilize the entire pond. Now, we did a little research and we determined a 4.5-foot clearance from the water surface elevation would allow for this. And this requirement did govern our design. So, now that we have vertical and horizontal locations determined, we turned our attention to pedestrian access. Now, we designed this with ADA, which is the American Disabilities Act in mind, and also to work within the space we had available. We turned to a slope bridge on the outermost two spans, which you can see on the left-hand side there. This slope was slightly less than 1 on 20, allowing, again, ADA, it was adequate for a continuous slope. That gave us about 2.5 foot of the 4.5 foot requirement. For the remainder, we looked at steps and handicap ramps, again, designed for ADA, including features like handrails and guardrails, things like that. And it would look very much like the rendering on the right-hand side.
All right, I'd like to start off by introducing the main purpose for each of these structures. The pedestrian bridge serves as a clear path for site tours. It also provides access to different locations on the site with minimal travel. The pier, a tourist feature, allows for fishing, as well as providing an assembly area with benches where the tourists could gather around, take pictures, and enjoy the beautiful scenery of Vermilionville. Now, before going into any design features, I'd just like to walk us through a little bit about our structured type, as well as material selection process. As a team, we sat with the clients to get a clear idea of exactly what client expectations were. And of course, as we expected, their number one priority was structural integrity. However, they did want us to design structures that would be aesthetically pleasing to Vermilionville, as well as provide them with some form of value engineering. We provided the client with a packet consisting of different structure type designs with different materials, as well as a cost breakdown for each. And after careful consideration of all these options, it was decided that we would design wooden structures using Southern Pine No. 2 as the main material. This material is both readily available and cost-effective in the region that we'll be designing for. Now in this slide, I have a visual representation of exactly what loads the structures would support, where these loads are coming from, and how each individual member that we had to design for would support these loads. The 90 pound per square foot is a pedestrian live load that would represent the weight of the individuals crossing the surface. 17 pound per square foot is a wind load calculated using wind factors based off of the designated region and designed for. And the 200 pound load in each direction is a concentrated point load that the guardrails would be designed to resist in order to provide rigidity for the structure, as well as an additional factor of safety for the pedestrians. Now, all these loads are minimum requirements based on the International Building Code, the American Society of Civil Engineers, and the AASHTO Design Guide for Pedestrian Bridges. Now, I'd like to highlight a little bit about each of the members that we had to design for and what role they play in supporting the structure. In purple, we have the deck boards, which will serve as the main walking surface for the pedestrians. The loads that act on the deck board would then be supported by these 5 beams shown below, referred to as stringers. The loading acting on the stringers, as well as the self-weight, would then be transferred onto the green beam here, which would be referred to as a bent, which would then be held up by these 2 gray-looking columns known as pile supports. The piles would be driven deep into the ground to provide enough resistance and stability to uphold the entire structure in place. Now, our design procedure was all done in accordance with the National Design Guide specification for wood construction. All of the members that we had to design for that I highlighted in the previous slides were analyzed as bending members. These are the deck boards, the stringers, and the beds. As a result of that, the member sizes were selected to satisfy 3 design parameters. These parameters were flexure, shear, and deflection. Flexure design states that the bending strength of a member must exceed the bending stresses that act on it, as shown in that figure. Shear design states that the shear strength of a member must exceed the applied shear stresses on that member. Now, shear stresses are the stresses that act parallel to a material surface, as shown in the figure below, caused by the loading that acts on that member. Finally, the International Building Code dictates that the maximum deflection that a member can experience must not exceed 1/360th of the member length.
All right, so these are some example calculations we use to size some of our members. The equations highlighted in yellow represent our design values, and the equations following compare design values to that of the worst case scenario with respect to whichever parameter we were checking. So as long as these equations yield a positive result, then our design is satisfactory. However, multiple designs can satisfy these criteria, so in order to determine the best one, we got cost estimates for each one, and then finally we selected the most cost-effective option. Now moving on to the design of the guardrails, which were used for both the fishing pier and the pedestrian bridge. Code dictates many of the requirements for them. So there's a minimum height requirement of 42 inches with respect to the top of the walking surface. There's also an opening limitation, which basically means that a 4-inch spear should not be able to freely pass through any of the openings located throughout the guardrails. Pickets must be able to withstand a 125 pound per square foot pressure. And finally, the guardrails themselves must be able to withstand either a 50 pound per linear foot distributed load or a 200 pound concentrated point load applied vertically or horizontally. On top of that, the guardrails must be able to withstand the pressure from the wind and support their own self-weight. So taking all that into consideration, this is a visual of what a typical section would look like for our guardrails. Now moving on to the design features of the pedestrian pier, we went with a total length of 192 feet, which consisted of 12 16-foot spans. For the first 11 spans, the width was 12 feet wide, and the last span was a dedicated assembly space to hold around 25 to 30 people for tour groups. And we believe with a 24-foot by 16-foot section, that would be adequate for up to 32. As for the design of specific members, we used 2x12 deck boards to support the loads from the pedestrians. Those loads, along with the guardrails, were transferred to 7 4x12 stringers, and finally, all of that was supported by one 8x10 bin.
The pedestrian bridge design features that will be discussed here include members' sizes that were selected to satisfy the design criteria that we discussed in previous slides. The pedestrian bridge would be 130 feet long, 8 feet wide, and it would be a 5-span bridge with each span running 26 feet long. The decking would consist of 2-inch thick by 12-inch wide deck boards at 8 feet long each. These deck boards would then be supported by 5 stringers. Each of the stringers would be 16 inches thick and 10 inches wide, 26 feet long. This would all then be supported by 9 feet long, 12-inch by 12-inch beds. In this slide, I have another visual representation of the loadings that would act on the beds for the bridge and the pier, and the exact compression loads that each of the piles would be designed to support. The pedestrian bridge was designed to have 2 pile supports, and the pier was designed to have 3. This was done so that the maximum compression load per pile was at a minimum.
I've taken the maximum loads from both the pier and the bridge, as well as the pile capacities, calculated using the geotech data from the boring logs. We're able to see how far deep we need to go with these piles to hold these loads, as well as what pile diameters we need to use, 6 to 8 inch or 7 to 12 inch. A quick note, 7 to 12 inch means a 7-inch tip with a 12-inch butt, so it's more like a cone shape. To help y'all visualize, pile capacity consists of skin friction resistance QS and point bearing resistance QP. You add these two up and apply a factor safety of 2, and you have the compressive capacity of each pile varying with depth. So at 30.3 feet, this load from the pier, 18.87 kips, equals the pile capacity of a 7 to 12 inch diameter pile. And at 35.5 feet equals the capacity of a 6 to 8 inch pile. We went with the more applicable 7 to 12 inch pile at a minimum depth of 31 feet and a recommended depth of 35 feet. Take a look at the cross section of the bridge with its load of 18.9 kips. You can see at 30.4 feet that this 18.9 kips equals the capacity of a 7 to 12 inch pile, and at 35.6 feet it equals the capacity of a 6 to 8 inch pile. To stay consistent, we went with the more applicable 7 to 12 inch diameter pile at a minimum depth of 31 feet and a recommended depth of 35 feet. At this depth, we can ensure sustainability of both the pier and the bridge's foundation.
Now let us talk a little about the erosion pond. Currently, the erosion pond has diffusers, bubblers, and water fountains, and these water features are important for us, for BBD to increase the dissolved oxygen level within the pond. Therefore, our client intends to remain these water features in the pond to maintain a proper level of dissolved oxygen to support aquatic life within the pond. In order to prevent stagnation within the pond, our client also intended to redirect the flow of water around the fishing pier before it ultimately discharges into the drop inlet. In order to achieve this flow redirection, we propose to attach fiberglass panel to the west side, along the west side of the fishing pier. The fiberglass panel that we recommend to use is fibercore panel from Fibertech. It comes with an exterior gel coating which provides resistance to UV degradation and weathering effect. In addition, the manufacturer also certain that their panels is rot-proof and corrosion resistant, and ultimately the lightweight nature of fiberglass panel drives us into making this recommendation. To get a better idea of where the fiberglass panel will be installed on the pile, this diagram shows the front view of the west side of the pier. As you can see here, each fiberglass panel is of 16 feet long and 5 feet wide and 3 millimeter in thickness. The fiberglass panel will be secured at water surface elevation, and if you look at the diagram again, there will be a space between the fiberglass panel and the bottom of the erosion pond, where the mud eye will be. The reason for this gap is to allow some of the water to flow under the fiberglass panel to prevent stagnation of water under the fishing pier. In order to secure the fiberglass panel on the fishing pond, we propose to use a hot dip galvanized U section. The reason we chose this section is due to its availability in the market and the nature of hot dip galvanized steel being corrosion resistant. To get a better image of how the U section will be used to help us secure the panel to the pile, this diagram shows the proposed placement of U section onto the different section of the piles. As shown in the previous slide, on the intermediate pile, we will have 3 U sections spaced at 20 inches apart. On the diagram, on the right hand side of the diagram, this shows the proposed method of attaching the whole system on the pile.
Currently, there are 3 existing aeration units as well as a fountain feature located within the aeration pond. Assuming that only half the pond will be aerated due to the flow diversion by the pier, at an average temperature of around 68 degrees Fahrenheit and an approximate water depth of 8 feet within the aeration pond, we determined that the existing 3 aerators need approximately 40 hours to raise the dissolved oxygen levels from 3 milligrams per liter, which is a typical value found in the summer months from the Vermilion River, to our recommended number of 5 milligrams per liter within the pond. At our proposed design flow rate, the water entering the pond spends approximately 15 hours of retention time, and to raise the dissolved oxygen levels from 3 to 5, we would need an additional 4 aeration units to make a total of 7. So kayakers beware, white water's ahead.
So now let's talk about the aeration pond drop inlet. The existing drop inlet on site has an elevation of 6.38 feet NAF88. We are proposing to drop 6 inches. We are proposing to drop the inlet by 6 inches, thus gaining us approximately 1.3 acre feet of storage. This gain in storage is vital for us to fulfill the no net fee regulation. As shown in the previous slide, the existing the existing drop inlet has a flat grade that is often being clogged up by plant debris. In order to alleviate this issue, we propose to replace the flat grade with a dome grade that provide a larger surface area for water to be discharged into the drop inlet. The water that is discharged in the drop inlet will be discharged into this ditch before flowing into the Petite Bayou. Therefore, erosion control in the ditch is as important. In order to minimize the effect of erosion at the ditch, we propose to line 200 feet of riprap along the ditch. We believe this will minimize the erosion effect.
As water enters the Petite Bayou, it reaches the end of our research park. Currently, the only way water can get out is via 2 stormwater pumps within Vermilionville. It is our objective that for any water that we introduce to the park, not have to use these pumps. We will do this via a passive outlet. The location of our outlet will be at the northeast corner of the Vermilionville village. Here, a levee separates Petite Bayou from the outlet ditch which leads to the Vermilionville River. We propose using concrete culverts along with grading to keep out any debris or critters that it may encounter. The flow potential through the culverts will be dictated by the inflow towards the culverts as well as the water surface elevation of Petite Bayou and Vermilion River. Taking a look at the profile view of our passive overflow, we see that the designed water surface elevation of Petite Bayou is roughly 5 feet. With the help of our headgrass model, we recommend setting 2 2-foot diameter concrete culverts at an invert of 4.02 feet. With a 0.3% slope, this will allow us to discharge our maximum flow of 3,450 gallons per minute. The Petite Bayou will be able to discharge so long as the Vermilion River is below 5.11 feet. As the river rises from 3.87 feet, however, we will have to mitigate backflow. We recommend doing this with a duckbill check valve. We selected this device because of its low cracking pressure as well as its low head loss compared to other backflow prevention devices. Furthermore, it requires little to no maintenance and is able to seal around small amounts of debris while still preventing backflow from Vermilion River to Petite Bayou.
Now we will talk about the headgrass model. First of all, what is headgrass? It is the Hydraulic Engineering Center's river analysis system, hydraulic modeling software widely used by engineers. We use this software to verify our hydraulics designs and also predict the behavior of the water features during storm events. Here you can see a visualization of the headgrass model in a profile plot, and the water features are shown in order of flow direction. First, the water enters the swamp and exits here through a culvert under the service road into the pond, where it leaves through the drop pipe into Petite Bayou, and it finally exits through our proposed passive outlet into the Vermilion River. 2 models were ran, one for the existing and one for the proposed structures. Here are the outputs of the existing model. The flow shown represents a 25-year design storm with the existing stormwater pumps running as intended in the original plans with a float set to 5.38 feet. You can clearly see that the water overtops the banks in the north side of the swamp, showing us that we need to build up a berm to retain the storm water. And now, to avoid confusion, this image is flipped from images seen before, and this is just because HECRES was being stubborn and wouldn't let us flip the image in animations. But you can still clearly see, not anymore, the road here, showing us the need to raise the road and redesign the culvert underneath. In the proposed model, the shown flow is 3,450 gallons per minute, our maximum design flow, and the existing stormwater pumps are not in use. As you can see, the fluctuation in the water surface elevation is minimal, and a better view to visualize these is the profile plot, where you can see that the water will fluctuate about half a foot throughout our day-to-day pumping operations, and it will peak at 5.16 feet in Petite Bayou. Now to the results of our design. In the 25-year storm, in our proposed design, the road will not be overtopped anymore. Also, the stormwater in the swamp is contained by the banks, and we have created more storage by dropping the draw pipe from 6.38 feet to 5.88 feet. Finally, HECRES also gave us an idea about the usage of the existing stormwater pumps. Currently, these pumps are ran manually, which made it hard for us to estimate the pumping hours. This will be changed. In our proposed conditions, the pumps will not be running in the day-to-day operations due to the flow being set higher in Petite Bayou than the water surface elevation, and they will only be running for about 1 hour and 50 minutes during our 25-year design storm. Again, we've created some storage by dropping the pump float by 0.13 feet from 5.38 feet to 5.25 feet, making our design more predictable, economical, and most importantly, less likely to flood.
We were really hoping Franz would do a little bit of that in German. Now we'll switch gears from hydraulics back to structures. I'm going to discuss a little bit about the water resource park building. Shown here in yellow is the approximate location of the building. Right here we have an architectural rendering provided to us by Mr. Guidry, who is the architect currently working on the structure. This structure is going to be utilized for two purposes. First, on the right-hand side here will be a watershed exhibit space, and on the left-hand side will be a laboratory and office spaces. Typically, a structure of this type will be designed by a code called IBC, which is the International Building Code. Now, IBC is a prescriptive code. For most situations, it will require, it will give you minimum member sizes and spacings, things of that nature. And this building will be designed in that method. Some might be asking, might be thinking, well, what did y'all do? Fortunately for us, this building has several components that fall outside the limitations of this code, specifically being the roof structure above the exhibit space. Is a very large span, it's a very large open space, and the floor systems. The floor systems is due to the loadings that will be applied to that system. And the other task we had was to analyze the building as a whole to come up with loadings on the power foundation so we can do power design.
So ASC 710 and the International Building Code required that the exhibit side of the building be classified as an assembly space with a recommended live load of 100 pounds per square feet, and the laboratory side of the building be classified as an office space with a recommended live load of 50 pounds per square feet. Now, in order to conduct our wind loading analysis of this building, we basically considered two systems and split the building in two. This gave us two idealized models to conduct our wind loading analysis for various wind loading conditions. 8 load case combinations were
used in our analysis, and the one that yielded the highest loading results, which was the worst case scenario, governed our design. Now, this is what we used to design our members. Now, what we chose was Southern Pond number 1, and the national design specifications for wood construction was utilized throughout our design process. And the main strengths checked were that of bending, shear, tensile, and compression perpendicular and parallel to the grain of the wood. And we had to make sure that the loads we calculated previously stated remained less than that of our design loads. So we checked every single one of them as stated. And it's important to know that, well, this would prevent failure in even the worst case scenarios. So it's important to know that wood is not a homogeneous material. It's not uniform throughout, which means that it splits easier one way, as shown. That's why you chop wood like that and not the other way. So the tensile stress, if a tensile load was applied along the grain parallel to the grain of the wood, it resists a lot better, and perpendicular, not so much.
So we compiled all these analyses and load determinations into a computer model. We use a software called STAC, which is an acronym for Structural Analysis and Design. Now, we use this model for a couple of reasons. One, to verify our hand calculations, and two, to analyze the structure as a whole. On the right-hand side here, you have a rendering of what we were looking at in the model. Now, all the materials that you don't see here were applied to the model as loadings. Here you see a screenshot of what I was working with. Surprised I didn't go blind looking at this. Each one of the black triangles is a pile location. Now the pile locations were determined by, we did two things. We placed piles directly underneath the bearing walls, and we also equally distributed loads in the large spaces. On the right-hand side, you'll see all the load cases we analyzed, and on the left, you'll see an example of one of the piles, the results that the software produced for one of the piles. And highlighted here in red, it was the worst case scenario. A couple of facts about that worst case scenario. The average loading on each pile was about 8,700 pounds, and the peak underneath some of the load-bearing walls was about 19,000 pounds. The building as a whole, unfactored, the basic weight of the building was about 113,000 pounds. We took all this data, compiled it, and we used that to, as I said, analyze the design of the pile foundations.
Following the structural analysis, the next step was a geotechnical analysis to determine how deep each of the piles must be embedded into the soil layer below to ensure proper capacity so that the structure remains intact. Shown here is a crane driving a pile into the subsurface strata via hammer, and it was decided that each pile would go under each of the triangles shown in the graphic here. Throughout geotechnical calculations, it was decided that the most effective bearing depth was 25 feet below grade to ensure that each of the 7 to 12 inch diameter piles would be capable of supporting the loads imparted by the structure in even the most extreme loading cases.
So with the addition of the aforementioned WRP building, the existing parking lot on site would have to be redesigned. We wanted to do this in a way that would minimize the loss of parking on the existing parking layout. So to do this, we needed to look at the existing conditions in that parking lot.
Okay, briefly, we'd like to display all the parking existing in the BVD project area.
Shown here in black is the location that will ultimately serve as the BBD Education Center building parking. In blue here is Vermilionville parking, and in green finally is Fisher Road adjacent parking that is excess parking for both the BBD and Vermilionville. We are proposing that all surfaces within this location be resurfaced and restriped, with the exception of 4 demonstration areas of pervious pavement that BBD have installed as an educational display. Expanding on the parking lot that will see a redesign. Currently we have 155 parking stalls, none of which are handicap accessible. Also noted is that in the current layout, a bus is not, this layout does not accommodate a bus traversing this parking area.
So as shown here, we have our proposed design for the parking lot layout. This parking lot is going to consist of 111 total parking spaces, which is 44 less than what's currently existing. Of those 111 spaces, we have 106 standard stalls, as well as 5 handicap accessible stalls. So you might be wondering what's going on in the video here on the screen. That's actually our design vehicle, which is an Ashito extra large school bus traversing the parking lot. Through the use of an extension of a program called Civil 3D, we were able to plot the vehicle's path in our parking lot and check to see if there were any conflicting points in this parking lot. So as you can see from this video, the bus is able to traverse the parking lot layout, so our design is adequate. One of the next things that our client requested us design was a walking path to show off some of the new water features that are going to be added to the park. The walking path highlighted in yellow is approximately 1,200 foot long and will be comprised of mostly wooden members. And this is to keep with the aesthetic of the park, as well as combat the cypress knees in this area of the pond. We're also proposing that this walkway be elevated approximately 1 to 2 inches above grade to allow stormwater to pass underneath it.
So as you can see here, we have this beautiful 3D rendering of the proposed design of the wooden walkway. This walkway was designed to comply with the international building codes. According to ADA compliant, ADA required a minimum of 3-foot width for any kind of walkways or accessways. We went ahead and designed this to be a 5-foot width in order to accommodate different pedestrian traffic from either sides. In this design comprises of 2x8 boards as stringers and beams, 4x4 posts as supports, 1x6 decking boards, and 1x4 boards for wheel stop. The design lumber species for this purpose is number 2 southern pine, pressure treated for ground contact to prevent it from rotting and from termites.
So we're going to conclude tonight's presentation by discussing some of the permitting requirements that come along with this project, and then detailing some rough construction cost estimates that we developed. So because of the nature of this project, there were permitting requirements at the federal, state, and local levels. I'll begin by highlighting a few of the main federal permitting requirements. First, USACE, or the United States Army Corps of Engineers, who require a permit for all outfall structures and associated intake structures where the effluent from the outfall pipe is regulated by the National Pollution Discharge Elimination System. Next, FEMA, or the Federal Emergency Management Agency, who require a permit for all development or construction within any special flood hazard area. Being that our site is within an AE flood zone, we are within that special flood hazard area. Therefore, a permit must be obtained from FEMA before development can begin. Lastly, because we are within such close proximity to an airport, the FAA, or Federal Aviation Administration, requires that a construction notice permit be filed before certain construction activities can begin. I'll move on and talk about some of the more important state and local permitting requirements on the following 2 slides. So at the state level, an important category of environmental permits that must be considered for this type of project are water discharge permits, which are issued by the Louisiana Department of Environmental Quality. Temporarily, a construction activities water discharge permit, which authorizes temporary stormwater discharge from construction activities, must be filed. Permanently, a general water discharge permit, which will authorize the stormwater discharge from our passive outlet, must be filed and maintained for the entire life cycle of that outfall structure. So in addition to state and federal permitting requirements, we also had to ensure that our project was in compliance with local ordinances. For instance, LCG's Unified Development Code, or UDC. So a few of the UDC requirements. First, the UDC requires that on-site drainage improvements accommodate the entire upstream drainage area, whether that's inside or outside of the new development. The size of the watershed being considered in our hydrologic design calculations does satisfy this requirement. Next, the UDC requires that engineers evaluate the effect of a development on existing drainage facilities. We were able to conduct this evaluation by running the pre and post hydraulic models that were discussed earlier in the presentation.
All right, so lastly, we were able to come up with a construction cost estimate for how much it would cost to build a water research park. On the left-hand side of the screen, you can see a table with a breakdown of how much certain features would cost. I'm going to highlight a couple of them for you. The pump station is going to pump the water from the Vermilion River. It costs about $200,000. The fishing pier comes in at about $110,000, and the pedestrian bridge comes in at about $165,000. You add up all the costs within this chart, and the water research park alone comes up to a total of $760,000. The construction cost for the water research park building was given to us by BVD, which comes from the architect of about $850,000. We were able to confirm that the foundation itself comes in at about $60,000. If you put a 20% contingency on that, and you come up with an extra $300,000 and engineering fees to be $200,000, your final project cost comes just over $2.1 million. All right, so now I'd like to thank everyone for coming out tonight and give a special thank you to BVD for allowing us to work on this project and allowing us to present on their grounds. Special thanks again to Emil Onstelet, Wesley Davis, and Lauren Carter. We also want to thank all of our mentors again. Mr. Chris Richard with Domain Zavo, Glenn McCall with Finstamaker, Ms. Megan Foray with Huvald Associates, Jared Bro with Site Engineering, and Fred Trahan and Allison Loignon with Lafayette Consolidated Government. We also want to thank all of our faculty, our civil engineering faculty that has provided us all this knowledge throughout the past few years. A special thank you to Mr. Sharp for putting up with us this semester and guiding us through the senior design process. And also a special thanks to Dr. Robert Miller for his hydraulic design, assistance on the hydraulic design. All right, again, thanks for everyone for coming out.